Okay, guys, this is a review for limits. I think I went over some of these problems in class, but I'm just gonna go over the whole sheet so you can prepare yourself a little bit. Okay, so here they want you to find the limit, right? Ignore this because we don't have that table. We just need to compute the limit, right? You want to factor the numerator because if we plug this straight, you can evaluate limits just by plugging it in, right? But if you plug this in here, you get, for the numerator, you get 27 minus, that will be also 27. And then this is plus 6 minus 6. So you can see you get 0 here on the numerator. And if you plug here in the denominator, you get 81 minus 3 cubed is 27. 27 times 4, that's 108. And then this is 118, and this is 9. So if you add this, you get 90. This is 108. So you get this 0 over 0, right? So we cannot evaluate the limit directly. So we need to factor, basically, right? So if possible, right? Because that's sometimes you can't, right? But let's try to factor it here. So you can do factoring by grouping here, right? You know how to do that. So this is x squared, x minus 3 plus 2, x minus 3, right? So the factor form will be this, right? So that's a numerator. So we're good. We don't need this anymore. Okay, let me erase this. So this is my numerator now. Sorry. Okay, so now I need to factor the denominator if possible. So factoring by grouping is not going to work on the denominator. So I need to do what? I need to do the rational root theorem, right? No choice. So you take the coefficients or the multiples of the constant, right? So this is going to be plus or minus 1, plus or minus 3. I'm talking about this, right? If you don't know what I'm talking about, I'm talking about this number. Sorry. I'm talking about this number right here. Sorry. I'm talking about this number. Right? So the multiples of 9 are 1, 3, 9, right? And then for Q, right here, you just have 1, right? That's the leading coefficient. So this is the constant, right? And this is the leading coefficient, right? So you take the ratio of those two and you need to find out, those are the possible values that will give you 0, right? For that polynomial. So we have, well, that's just 1, right? And anything divided by 1 is just itself. So that means these are the numbers. So you need to try to plug these numbers here in this denominator to see which one works, right? So I already did this. If you plug 1 here, you're gonna get these things, right? You need to get 0, right? Basically. So when you plug this 1 or -1, +3 or -3 or 9, or of -9, you need to get 0. Okay. So if you do that, you need to plug 3. Okay. So if you do this many times, you will see that it's 3. 81 minus 4 times this is going to be 27 plus 6 times 3 plus 9. That should give you 0 or -3, one or the other, right? So this is 81 minus 108 plus 18 plus 9. That's going to give you 0. So 3 is the factor that you need, or 3 is a 0, right? So if 3 is a 0, that means that this is x minus 3, and I need to use a synthetic division to find out what value, if I can simplify this further, right? So if I use 3, right, I get 1, -4. So I'm taking the constants of these numbers, right? So 1, -4. There's no x squared, so I have to put a 0 here, and then 6, and that's 9. So you drop the number, right? So this is 3, -1, -3, -3, -3, that's 3. Let me see if I'm writing this one, 84, 0, 6, 9. So 1, 3, -1, -3, -3, -9 here, right? -9 here, this is -3, this is -9, and you get 0. So these are This is your polynomial, right? So this is going to be x cubed minus x squared minus 3x minus 3. And if you do the rational root theorem again, it's not going to work out. So you have to plug here x cubed minus x squared minus 3x minus 3, right? So you can see that these they cancel. So you get x squared plus 2 over x cubed minus x squared minus 3x minus 3. So if you evaluate the limit as x equals 3 and you plug that in, you should get, okay, you should get, so 3, that's 11, right? And then here you have 27 minus 9 minus 9 minus 3. So that's going to be negative 18, negative 21. So that's going to be 6. So this is the answer. So this is the limit, right? This problem was a little ugly because of the polynomial that they gave us, right? But other than that, it will be a straightforward process. So make sure that you understand that, okay? The second one involves calculus. If you know calculus, you can understand what I'm gonna do right now. If you don't worry about it. That's not important at this point. So if you plug 0 here, you know cosine 0 is gonna be 1, right? And sine of 0 is 0. So this is gonna be 1 minus 1, right? Over 0. So this is 0 over 0. You have that in determinant form. You don't want that. So you need to take, in reality, you have to do L'Hopital's rule here, right? So the derivative of cosine is negative sine x. The derivative of the constant is 0. The derivative of sine is cosine. So now you can evaluate the limit. The limit as x approaches 0 of negative sine x. If you put 0 for sine, right? And 0 for cosine, you know cosine of 0 is 1. And sine of 0 is 0, so that's 0. So this limit is 0, right? But you don't need to worry about that, okay? Okay, here you need to evaluate the limit, right? So if you can just plug it in and it turns out to be a nice number, then you're good, right? So if you plug that in, you get 50 minus 20 plus 7. So that's gonna be what, 37, right? That's it. Just plug the 5 in the function, right? That's all. Here, same thing. If you plug that in, you get 4 plus 2, that's gonna be 6 minus 6. And this is gonna be 0, right? So 0 over 0 is an undeterminate form. So you need to factor basically, right? So if you factor that out, this is x plus 3, x minus 2, x minus 2, cancel, cancel. If you plug that in the simplified version, you get 5. So that's the limit, right? Next. Here you need to factor as well, right? So this is gonna be, because if you plug it in, you get 16 minus 24 plus 8. So that's 24. You get 0 over 0 again, right? So you cannot just leave it like that. So you need to factor basically. So this is x plus 4, x plus 2, and this is x plus 4. Cancel, cancel, plug it in, you get negative 2. Yes? Next. This one is x plus 1 to the second power. If you plug it in as the way it is right now, if you plug negative 1, you get 0. Negative 1 is going to be 1. And 1 minus 1 is 0. So you get this thing, right? Again, in determinant form. You don't want that. So you need to factor, right? So you have x plus 1, x minus 1. So if you simplify this, you get x plus 1 over x minus 1. You plug it in the negative 1, you get 0 over negative 2, which is 0. So this is the limit, 0, right? Because you have 2 copies of that and 1 copy of that, right? So this cancels once. Okay, next. Again, let's see if we plug it in and we get the nice number. So we get 4 minus 4. So that's going to give you 0 over 0 again, right? In determinant form. So we cannot do direct substitution basically, right? We need to factor. So this is going to be x plus 2, x plus 2, x minus 2. This is the difference of squares. So this is x over x minus 2. Plug it in, right? So you get negative 2 over negative 4. That's going to be 1/2. Okay? That's the answer. That's the limit. Next. Here, let's see if we plug it in. That's 4 minus 4. That's going to give you 0 over 0 again, right? 0 over 0. You cannot leave it like that. So you need to do some algebra. You need to multiply this by the conjugate, right? Or you need to rationalize it. Okay, so this is x minus 16, and then this is, okay, so this is x minus 16, and this is going to be x minus 16 times square root of x plus 4. So this simplifies with this one. You get 1 over square root of x plus 4. You plug it in, the x here, and you get square root of 16 plus 4, right? So that's 1 over 4, 1 over 8. That's the answer. Next. Let's see. Here, the same thing. I need to rationalize it. So this is going to be 9 minus x over, here I can just leave it like this, x minus 9, 3 plus the square root of x. But you can do some algebra on the numerator. You can say that this is the, if you factor the -1, you get x minus 9, and you get x minus 9, 3 plus square root of x, cancel, cancel. So this is going to be -1 over 3 plus the square root of x. Use the limit, right? 9. So this is going to be, you plug 9 here, right? If you plug 9 here, the square root of 9 is 3. So this is -1 over 6. That's the limit. Okay? That's it. That's all you got to do. So this is evaluating limits, right? Okay, here. Let me erase this stuff. So they're asking you here, evaluate the limit based on this graph, right? So they're asking you the limit as x approaches -1 from the left. So from the left means from here, right? This is your left. If you're watching this video, hopefully that's your left, right? So as x approaches -1 from the left, so you are going this way. So from the left is this graph. So you're approaching 1 from the left. Oh, I'm sorry, -1 from the left, not 1, -1. So -1 is here. So as x approaches -1 from the left, you're approaching this value, right? -3, right? So if you approach, as x approaches -1 from the left, you're approaching -3, right? The y value of -3. So this is the answer for that. So the second question, or B, is asking you as x approaches -1 from the right. So -1 from the right. This value is approaching also -1. So this is, sorry, approaching -3. Let me explain to you one more time. The limit as x approaches -1 from the left, you're approaching -3, right? The y value of -3. So this is -3. The limit as x approaches -1 from the right, the y value or the f of x is approaching also -3. Therefore, if the limit as x approaches -1 from the left and from the right is equal to -3, the limit as x approaches -1 from either side or for both sides is going to be the same as -3. Yes? Now they're asking you here, evaluate f of -1. So what happens when f is -1? Well, when f is -1, the value of that function evaluating at -1, that's going to be -3. So that's going to be -3. So that's continuous everywhere, right? Because the function is defined at -1, the limit from the left and the limit from the right exist. Therefore, the limit as x approaches -1 also exists. And since the limit as x approaches -1 is the same as the function defined at -1, therefore, this function is continuous at -3, right? If they're asking you that thing. So what is x of -1? I'm sorry, as x, the limit as x approaches 1 from the left. So now we are approaching 1 from the left. So if we approach 1 from the left, right, we are approaching the value of -3, right? From the left, we're approaching -3. You can see that from here, right? As x approaches -1, I'm sorry, as x approaches 1 from the left, that is approaching -3, right? the limit as x approaches 1 from the right, so we're coming this direction, we're approaching 2, so that limit is 2, right, from the right. So here you can see that there's a jump, right? So this limit is not going to exist. This is what they call jump discontinuity, right? And when you have a jump discontinuity, that's a non-removable discontinuity, okay? If you have a hole, that will be a removable discontinuity, right? But if you have a jump discontinuity or an asymptote, right, then that means that that's a non-removable discontinuity, okay? So here they said the limit as x approaches 1 from the left is approaching -3, and the limit as x approaches 1 from the right is approaching 2. So these limits, they don't match, right? This one, sorry, this one, and this one, they don't match. Therefore, the limit as x approaches 1 does not exist, right? And now they're asking you, what is the function at 1? Or what is f of 1? Well, you cannot say is this one, right? You can't, because there's a hole here, right? But it's defined here, because that you see the little dot is closed, right? So it's defined at that point. So f of 1 will be 2, right? So f of 1 is 2. Okay. Now, they're asking you the limit as x approaches 4 from the left. So 4 from the left. So 4 from the left, it means this thing. So you're approaching -1, right? From the left. The limit as x approaches 4 from the right, you're approaching 0, right? Okay. Since the limit as x approaches 4 from the left does not match with the limit as x approaches 4 from the right, I'm talking about this, right? Since these limits, they don't approach the same value, therefore, the limit as x approaches 4 from either side does not exist, right? Because they're different. And what is f of 4? Well, let's see. F of 4, what is the function value f of 4? When x equals 4, what is the y value? 0. Okay? That's how you do these things. Let's continue. I should not erase that. I should just erase this. Okay. Let me erase this thing. So they're asking you, determine whether the given function is continuous at that specific value of x. Remember to use the all 3 tests to justify the answer. This is the 3-step continuity test, right? So if the function is defined at a specific value and the limit from the left and the limit from the right approach that same specific value as well, then and the limit from as x approaches that value is the same as the function value at that, for example, here, let me reword that. If the function value, or basically if f of that number equals some value, and the limit from the left equals the limit from the right, then that means that the limit exists. And if the limit as x approaches that specific value is the same as that function value, then the function is continuous everywhere. That's what this thing is saying, right? So let's do an example, and then it will make a lot of sense. So they're asking you, determine whether f of x is continuous at x equals -1. So I'm not gonna use this because they're saying that x is less than -1, so I have to use this one, right? When x is less or equal, I'm sorry, x is greater or equal, right? So I'm gonna use that. So if I plug it in, I get f of -1 equals -5 over -2, right? So that's gonna be 5/2. So that's the value of f of -1, right? It's 5/2. So now that implies this condition, the first one, right? I'm doing this one. I'm just checking what's the value of f equals -1, right? Now, I need to check what happens from the left and from the right, right? And if that holds true, then the limit exists. And then if the limit exists and is the same as that function value, then the function is continuous at that specific value, right? So I need to do from the left. So from the left, I have to use this one, right? Less than -1. So let's plug it in. So f of -1. So that's going to be -1 to the second plus -1. And then this is going to be -1 plus 1, right? If I'm doing from the left, right? But before I do that, I have to be careful here, because if you see here, you can factor this value, and this is x plus 1 and x plus 1. So these, they cancel. Remember, this is a rational function, right? So if you have something after you factor that the numerator and denominator, some, in this case, so this expression cancels with a 1 below, then you have a hole at this value, right? At x equals 1. So that means that that's a discontinuity, right? In that function, right? So at x equals 1, there's some kind of discontinuity in which we call a hole, right? Now, if you do like the limit from the right, or what happens to the right of this function, we have to use again this. And we already did that before, right? When we plug -1, we get 5/2. So you can see clearly that the limit from the left and from the right kind of don't match, right? So if that situation happens, then that limit does not exist. So therefore, we are violating this rule, right? Rule 2. Therefore, we cannot say that the function is continuous, right? That means that we have to stop and we have to say that the function, it's not continuous at x equals -1, because we have the hole in there, right? Okay, so that's what happens there in this problem. Let's do this one. So this one, they said we have to do the same thing, the 3-step continuity test. Okay, so if we evaluate the function at 6, well, that's already given. So they're saying that f of 6 is 29. Okay, so it's defined. So condition 1 is satisfied. Now let's do let's see what happens to the left and to the right, right? So to the left of 6, I have to use the first one, right? So if I plot f of 6 of x squared minus 7, I need to plug 6 here, and you get 36 minus 7, which is 29. So that will be kind of the limit from the left. Now, if I do from the right, f of 6, that should be 3 times 6 plus 11. That's 18 plus 11. That's 20. That's 39. I'm sorry, 29 as well. So you can see from the left and from the right is the same thing. Therefore, the limit as x approaches 6 for this function is 6. I'm sorry, 29. Since condition 2 is also satisfied, let's see if the last condition is satisfied. The limit is the same as the function defined at that value. So we have f, the limit as x approaches 6 of f of x equals f of 6. And indeed, it's the same, right? Because we have the limit is 29 and the function defined at 6 is 29. Therefore, the function is continuous at that specific value, x equals 6, right? So that's how, so therefore the third condition is also satisfied. So that's how you can check if this function is continuous or not, right? Okay, so that's that. Let's continue. So here they're asking you, determine whether the function below are continuous or discontinuous. If there exists a discontinuity at that point, identify the discontinuity as removable or non-removable. So I explained that before. I need to check what happens here, right? So I have to factor this out, x plus 3, x minus 3. And here I'm gonna get x minus 10, x plus 3. So this cancels, so you get x minus 3, x minus 10. Now, because you cancel the numerator and the denominator, right? That means that we have a hole, right? There's a hole at x equals -3, right? And what else? I need to check what is the I need to check what is the horizontal asymptote, right? The horizontal and the vertical asymptote as well. If there, so for the vertical asymptote, it should be 10, right? So we have at x equals 10, we have a vertical asymptote. And the horizontal asymptote, just remember from the rational functions that since the degree of the numerator is the same as the degree of the denominator, these values, you just take the ratio of the leading coefficients and you get 1, right? So that means that the horizontal asymptote is defined at y equals 1, right? Okay. And yeah, that's it, right? Okay, so if you want to graph this to see what happens, you can say, well, there's an asymptote at x equals 10. So let's say that 10 is around here somewhere. So this is the asymptote. And there's horizontal asymptote at y equals 1. So that's around here, right? And we have a hole at x equals -3, right? So if we want to find the order pair, so that would be, I need to plug it in this, simply in the reduced version of the rational function, right? So if I plug f of -3 here, I will get my y value. So that's going to be -6 over -13, right? So that's going to be 6 over 13. So if you do that, it's 0 point something, right? So that's going to be here. Let's say -3 is here, and that hole should be around here somewhere, okay? So the graph should look something like this. So now, what you can say, well, this one, the hole, is a removable discontinuity, right? Yes, and the vertical asymptote is a non-removable discontinuity, right? And if you see a jump, it's also non-removable. Okay, so if the coordinates or the order pair for the hole is a -3, 6 over 13. Okay, if you want to state it, where is the hole, right? The hole is here, right? That's the coordinate of the hole. And that's it. That's all you gotta do, right? That's all you gotta do. Definitely it's not continuous, this function, right? It's not continuous. Okay, let's continue with the next question. So this one, they're asking you here, determine whether the function below are continuous or, okay, same question, right? So I need to, okay, so first of all, I need to find my vertical asymptotes, right? So I cannot factor anything on the top, or nothing on the top is going to cancel with anything on the bottom. So this is going to be x plus 5, x plus 1. Nothing cancels. But there's two vertical asymptotes here. Vertical asymptote at x equals -5, right? X equals -1. So you do your graph, right? So that's going to be -5 here, -1 here. You do your line. Is it a horizontal asymptote? Well, since the degree of the denominator is higher than the degree of the denominator, the degree of the numerator is less than the degree of the denominator, the horizontal asymptote in this case will be 0, okay? That's like a rule that you need to remember, or you can take the limit as x approaches infinity, and you will see that since this is bottom heavy function, then this will increase faster, the denominator. So you're gonna get a bigger number over a smaller number, and you know when you have a bigger number over a smaller number, it goes to 0, right? So you can do that. Okay, so what else I need to do? I just need to graph the function, right? So you know that these are the points of discontinuity, right? So this is a non-removable discontinuity, right? Every time you have asymptotes, vertical asymptotes, those are non-removable discontinuities, right? Okay. And now you graph this thing, right? So you graph it, the horizontal asymptote is a 0. So when you graph it, it looks something like this, I guess. Something like that. And then here is something like this. And I believe here was something like this. Okay. You can just use any number to the left to find out what is the behavior of the graph. Okay. I think it was like this. Okay. That's it. That's all you gotta do for this sheet. Okay. I hope this helps. Please watch this video again and try to understand what's going on. Watch it as many times as you need. I'm gonna post another one maybe in like the next 1 hour, so you guys can practice. Okay. Have a nice day. Thank you.